1 second. That is how far the evidence reaches. Every direct measurement we have of the birth of the universe, the oldest light in the sky, the helium inside every star, the deuterium in a glass of water, takes us back to about 1 second after what we call the beginning, and not one step further. The largest machine ever built gets us to a trillionth of a second. Past that, nothing at all. No data, no observation, no instrument anyone knows how to construct. But here is what they leave out of every explanation of this you have ever been given. The moment when time is supposed to have started sits another 31 orders of magnitude below that floor, in a stretch that has never been tested and may never be. If the universe is infinite, and the measurements permit that, then rewinding the expansion never compresses it into a point, not after a million steps, not after an infinite number of them. There is no cosmic clock waiting to be wound back to zero, and there never was one. And the physicists who wrote the equation that produces the beginning are by and large not the ones who believe in it. So did time start at the Big Bang? By the end of tonight, you will know exactly. Get comfortable. Hit subscribe if you're new here, because by the end of this, the beginning of time will sound like a statement about us rather than about the universe. Now, let's slowly ease into this. Part 1. The sentence everybody knows. There is a sentence you have almost certainly said out loud, or nodded along to, or written down in a school exercise book, and it goes something like this. The universe began 13.8 billion years ago, in the Big Bang, and time began with it. It is a good sentence. It is short, it is confident, and it has the particular shine that facts acquire when they have been repeated often enough that nobody bothers to check them anymore. Tonight we are going to check it. The full version of the story usually runs like this. About 100 years ago, astronomers discovered that distant galaxies are moving away from us, and that the further away they are, the faster they recede. That was interpreted, correctly, as expansion. Space itself is stretching, and everything that is not held together by gravity or by the forces inside matter is being carried apart on that stretching. Now, if the universe is expanding, then in the past it must have been smaller. Rewind the film. Everything gets closer together. Closer means denser, and denser means hotter, and if you keep rewinding, the temperature and the density climb without any obvious limit. Keep going far enough, and, according to the equations, everything in existence converges into a single point of infinite density, a singularity. That is the Big Bang. And because space and time are, in Einstein's theory, a single fabric, and because that fabric converges at the singularity, along with everything else, there is no before. Time starts there. Asking what came earlier is not a hard question that we have failed to answer. It is a meaningless question, like asking what is north of the North Pole. You have heard that comparison. We will come back to it, because it is more interesting and considerably less reassuring than it sounds. I want to be extremely careful about what is being questioned here, because this is not one of those videos. The Big Bang model is not in doubt. The evidence that the universe was once in an extraordinarily hot, extraordinarily dense state is about as strong as evidence gets in any observational science, and we are going to spend a good part of tonight looking at exactly how strong it is, and why, and where it comes from. I am not going to hedge on that. Two entirely separate lines of evidence, gathered with entirely different instruments by people who were not trying to agree with each other, converge on the same picture, and they agree to within a few percent. That picture is not going anywhere. What is in question is one sentence inside the model. The last one. the one about the final instant. Because here is the thing about that final instant. If you take that whole chain of reasoning I just laid out, and you go to the people who spend their working lives on it, the cosmologists, and the relativists, and the people who actually write the equations, and you ask them whether all of space was once compressed into a single point, and whether time started there, you do not get the confident sentence back. You get something much more careful, and often something considerably stranger. The picture that almost everyone carries around in their head is not the picture held by the people who built the theory that produced it. That is a peculiar situation, and it is worth sitting with for a moment. This is not a case of a fringe theory challenging an established one. It is a case where the popular version of a scientific idea and the professional version of the same idea have quietly drifted apart over about 60 years without anybody announcing it. Some of that drift starts with the name. The phrase "the Big Bang" was not coined by Einstein, or by Lemaître, or by any of the people who worked out what the equations were saying. It was used by Fred Hoyle on BBC Radio in 1949. Hoyle did not believe in the model. He was the leading defender of the main competing idea, in which the universe had no beginning at all and simply looked the same at every moment, forever. He later insisted the phrase was not intended as mockery, that he was just reaching for a vivid image for a radio audience, and he may well have been telling the truth. But whatever he intended, the name stuck, and it has probably done more damage to public understanding than any other 3 words in the whole of physics. It has done that damage by smuggling in 2 ideas, neither of which is part of the theory. The first is that there was an explosion. There was not. An explosion is material, flying outwards through space, away from a center, into a region that was already there. Expansion is not that. Expansion is the distances inside space, getting larger everywhere at once, with no center and nothing to fly out into. Every galaxy sees every other galaxy receding, and none of them is at the middle, because there is no middle to be at. The second smuggled idea is that it happened somewhere. It did not happen somewhere. It happened everywhere, and we will see later exactly why that phrase, which sounds like poetry, is actually a piece of geometry with a precise meaning. So we have a story everyone knows, built on evidence that is genuinely excellent, ending in a claim that the experts largely declined to make, wearing a name that was invented by someone who thought the whole thing was wrong. Which brings us to the question on the table, and I want to state it as plainly as I can, because the whole of tonight hangs on it. Did time start at the Big Bang? Not, did the universe pass through a hot, dense phase? It did. Not, is the universe expanding? It is. The question is narrower and much sharper than either of those. Did the dimension of time itself have a first moment, an earliest instant with nothing before it? And is that first moment the event we call the Big Bang? By the end of tonight, you will have the answer. I am going to give it to you plainly, and I am going to give you the reason behind it, which is more specific and more interesting than either a simple yes or a simple no. But I am not going to give it to you yet, because the answer only means anything once you can see the machinery underneath it, and the machinery is the good part. There are 2 pieces of that machinery, and you have probably never been shown either of them. The first is how cosmologists actually measure the size of the universe, which is not by measuring anything you would recognize as a size. The second is what it would technically mean for time to begin, which turns out to have nothing to do with clocks starting and everything to do with paths running out. Think of what we know about the origin of everything as a document. The early pages are dense with measurement, and they are legible, and they are astonishingly detailed. The writing continues, page after page, getting finer and more confident as it goes. And then, at the end, there is a last legible line. Everything up to it can be read. What we are going to do tonight is walk down to that line, slowly, and look very carefully at what is written there and at what is not. Because the strangest thing about the sentence everybody knows is not whether it is true, it is who does not believe it. Part 2. What we actually discovered 100 years ago. The discovery of the expanding universe is usually told as a single event with a single name attached, and almost every part of that telling is wrong. It was not one discovery, it was 3, made by 4 people across 17 years, and the man whose name is on it arrived comparatively late. It begins in Flagstaff, Arizona, at the Lowell Observatory, with an astronomer named Slipher. From about 1912, Slipher was doing something nobody else was doing, and doing it with a patience that is difficult to imagine now. He was taking spectra of the faint spiral smudges in the sky that were then called nebulae, and he was doing it on photographic plates that required exposures of 20, 30, sometimes 40 hours. Not 40 hours of work. 40 hours of light falling on a plate, accumulated across many nights, in an unheated dome, with the telescope tracked by hand and by clockwork to keep the smudge in exactly the same place for the entire time. What Slipher found in those spectra was that the light from nearly all of these objects was shifted towards the red end of the spectrum. In the language of the day, that meant they were moving away from us. And it was not 1 or 2 of them. It was almost all of them, and at speeds far higher than anything anyone had measured in the sky before. Nobody knew what to make of it, partly because nobody yet knew what the nebulae were. The question of whether these smudges were clouds of gas inside our own galaxy, or separate galaxies entirely, was still an open and rather bitter argument. Slipher had measured the recession of the universe before anyone was certain there was a universe out there to recede. Meanwhile, in 1915, Einstein had finished the general theory of relativity and had immediately run into a problem. His equations, applied to the universe as a whole, refused to sit still. They described a universe that expanded or contracted, and since everybody in 1917 knew perfectly well that the universe was static, Einstein added a term to hold it in place. He called it the cosmological constant. He was fixing a result that was not broken. In 1922, a Russian mathematician and meteorologist named Alexander Friedmann took the equations at face value. He worked out the full family of solutions for a universe that is smooth and looks the same in every direction. And he found that such a universe must be dynamic. It expands or it contracts. It does not sit still. He published, and Einstein read it, and Einstein published a note in reply saying that Friedmann had made an arithmetic mistake. Friedmann had not made an arithmetic mistake. He wrote to Einstein and explained the calculation. And to Einstein's considerable credit, he published a retraction the following year, agreeing that the solutions were correct. There is a surviving draft of that retraction, with a sentence crossed out. In the crossed-out version, Einstein said that Friedmann's expanding solutions, while mathematically correct, were physically meaningless. He thought better of it and deleted the line before publishing. It is one of the more revealing edits in the history of science, because it shows a man conceding the mathematics while still refusing the picture. Friedmann never saw any of it settled. He died of typhoid in 1925, at the age of 37, 3 years after publishing the solutions, and 4 years before the observations arrived that showed the universe actually behaves the way his equations allowed. Then comes Georges Lemaître, who is the most underrated figure in this entire story. Lemaître was a Belgian Catholic priest and a trained physicist and in 1927, working independently and apparently without knowing Friedmann's paper, he derived the expanding solution again. But he did something Friedmann had not. He connected it to the data. He knew about Slipher's redshifts. He had an estimate for the distances involved, and he pointed out that the observed recession of the nebulae is what an expanding universe would look like from the inside. He presented this to Einstein at a conference in Brussels the same year. Einstein's response, as Lemaître recalled it, was that his calculations were correct, but his physics was abominable. There is a footnote here that is worth having, because it explains why Lemaître's name is not the famous one. His 1927 paper was published in a Belgian journal with a small circulation. When it was translated into English for a wider audience, 4 years later, several paragraphs were missing, including the ones where he estimated the rate of expansion from the data. For decades, this was suspected to be some kind of suppression. It turned out, when the correspondence was finally examined, that Lemaître had cut those paragraphs himself, because by then he considered better measurements available and did not want to clutter the paper with a superseded number. He gave away his own priority out of tidiness. Edwin Hubble published the distance-velocity relation in 1929, using new distance measurements of his own, and, for the velocities, mostly Slipher's data. The relation was clean, and the case was made, and the expanding universe entered the textbooks under Hubble's name. In 2018, the International Astronomical Union voted to recommend that it be called the Hubble-Lemaître law instead. Slipher is still waiting. It is worth knowing how badly wrong the first version of the number was, because it tells you something about how this field actually proceeds. Hubble's original estimate of the expansion rate was too large by a factor of roughly 7. Run that rate backwards and you get a universe about 2 billion years old, which was a serious embarrassment, because geologists had already dated rocks on Earth to considerably more than that. For about 2 decades, the expanding universe implied a cosmos younger than the ground people were standing on. The error was in the distance measurements, and it took until the 1950s to find it. The lesson is not that the astronomers were careless. The lesson is that the expansion was established long before the number attached to it was trustworthy, and the two things are separate. And then, in 1931, Lemaître took the step that nobody else was willing to take. If the universe is expanding, he said, then run it backwards. Everything converges. And at the beginning, there must have been what he called the primeval atom, a single quantum containing everything, whose disintegration is the universe we live in. That is the moment the beginning entered physics. And I want you to notice exactly what kind of moment it was. The expansion is a measurement. Slipher measured shifted light. Hubble measured distances. Every improvement since then, and there have been enormous improvements, has been a better measurement of the same thing. That part of the story is data. The beginning is not a measurement. The beginning is an inference laid on top of the data, and the inference is simple. The equations that describe the expansion, extrapolated backwards past everything anyone can see, do something dramatic. Lemaître said so plainly. He was not claiming to have observed the primeval atom. He was claiming that if you take the equations seriously and run them all the way back, they hand you one. Everything we do for the rest of tonight is an examination of that single move. Not whether the universe is expanding, which it is. Not whether it was once hot and dense, which it was. Just how far you are allowed to run an equation backwards, and what happens to the sentence at the end when you find out. But before we can judge the size of that extrapolation, we have to know how good the ground underneath it is. Because if the evidence for the hot dense phase were shaky, none of this would be interesting. It is not shaky. It is some of the best evidence in science. and it comes from two directions at once. Part 3. The two things that cannot be argued with. I said I was not going to hedge on the evidence, so let me make the case for the hot, dense, early universe as strongly as it deserves to be made, which is very strongly indeed. There are two pillars. They were built by different people, using different instruments, measuring completely different physical phenomena, in different decades. They had no obligation to agree. They agree. The first pillar is the oldest light in the sky. When you look at anything far away, you are looking into the past, because light takes time to arrive. Look far enough, and you look back far enough, and eventually you reach a moment when the universe was not transparent. In the early universe, everything was hot enough that atoms could not hold together. Electrons roamed free, unattached to nuclei, and free electrons are extremely good at scattering light. A photon in that environment would travel a short distance, hit an electron, and be sent off in some other direction. Then again, light did not travel, it churned. The universe was not dark, it was blindingly bright and completely opaque, in the way that the inside of a cloud is bright and opaque. Then the expansion cooled it down, and at around 3000 Kelvin, something changed. That temperature is low enough for electrons and protons to combine into neutral hydrogen and stay combined. And neutral hydrogen, unlike free electrons, is nearly transparent to most light. Across a comparatively brief stretch of time, the fog lifted, and the light that had been churning suddenly found itself with nowhere to scatter and an entire universe to cross. That light is still crossing. It has been traveling ever since, and while it traveled, space stretched underneath it, and the stretching pulled its wavelengths out with it. It left as visible and infrared light, glowing like the surface of a cool star. It arrives now as microwaves. We measure it at 2.72548 Kelvin, just under 3 degrees above absolute zero. Here is the part that should get your attention. That radiation has a spectrum, meaning a distribution of energy across wavelengths, and the shape of that spectrum is a black-body curve. A perfect black-body curve. In fact, it is the most perfect black-body spectrum ever measured, anywhere, by anyone, including inside laboratories built specifically to produce good ones. When the measurement was first presented properly, the error bars on the data points were too small to draw on the graph, and the room gave it a standing ovation. Physicists do not generally applaud graphs. That perfection is not decoration, it is the whole argument. There is no known process that produces a spectrum that clean except matter and radiation sitting together in thermal equilibrium for long enough to forget any other history. You cannot fake it with scattered starlight, or with dust, or with anything else that has ever been proposed. To get that curve, the universe has to have been a hot, uniform, thermalized soup. The spectrum is a direct fingerprint of the condition the model says existed. The wavelengths have been stretched by a factor of about 1100, which tells you directly that the universe has expanded by that same factor since the light left. That is not an inference from a model, that is arithmetic on a measured redshift. And this light is not somewhere else. Roughly 411 photons from that event are passing through every cubic centimeter of space, right now, everywhere, through the room you are in, through the pillow under your head. Every second, an enormous number of particles of light that were released before there were atoms, before there were stars, before there was anything, are passing through your body without touching it. The discovery itself was an accident. In 1965, Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey with a horn-shaped antenna built for satellite communication, and they could not get rid of a faint hiss. It came from every direction, day and night, in every season. They checked the electronics. They checked for interference from New York City. They found a pair of pigeons nesting in the horn, evicted them, and cleaned out what their eventual paper delicately described as a white dielectric material. The hiss stayed. About 50 kilometers away at Princeton, Robert Dickey's group was building an instrument to search for exactly this signal, having reasoned their way to the prediction independently. When they heard what Bell Labs had found, Dickey reportedly put down the phone and told he remembered at the time was that the prediction had already been made and forgotten. Gamow, Alpha, and Herman had worked out in the late 1940s that a hot early universe should leave behind a relic radiation field of a few degrees. Nobody followed it up. The prediction sat in the literature for nearly 20 years, while the thing it predicted sat in the sky. The temperature of that light is the same everywhere, to about 1 part in 100,000. Once you subtract the shift caused by our own motion, which is about 370 kilometers per second in a particular direction. Hold on to that motion. It becomes important later, in a way you will not expect. That is pillar 1. Now the second pillar, which reaches much further back and is, if anything, more impressive. The microwave background shows us the universe at 380,000 years old. The light elements show us the universe at a few minutes old. In the first minutes of the hot phase, when the temperature was around 1 billion Kelvin, the whole universe worked as a nuclear reactor. Protons and neutrons were slamming into each other hard enough and often enough to fuse, and they built the lightest nuclei. Then the expansion cooled everything below the threshold for fusion, and the reactor shut down, and whatever had been made was frozen in. The theory of that process has essentially one adjustable number in it, the ratio of ordinary matter particles to photons. Fix that one number, and the theory predicts, with no further freedom, how much helium there should be, how much deuterium, how much helium-3, how much lithium. It predicts that about 24.5% of the ordinary matter by mass should be helium-4. When astronomers measure the most chemically primitive gas they can find, systems that have had the least contamination from generations of stars, they find between 24 and 25%. It predicts a specific amount of deuterium, which is hydrogen with an extra neutron, at a ratio of roughly 2.5 parts in 100,000. Deuterium is the sharpest test in all of this, because stars destroy deuterium and never produce it in meaningful amounts. Any deuterium anywhere in the universe is a survivor. It cannot have been made later. The measured abundance, taken from gas clouds, backlit